Did you know that for more than a decade, Bitcoin's entire security model rested on a piece of technology that wasn't even the first choice? Seriously, it was a workaround, a practical fix that ended up defining an era of cryptocurrency. Today, we're going to pull back the curtain on ECDSA, the elliptic curve digital signature algorithm, and uncover the incredible story of Bitcoin's accidental signature.
All right, let's get into it. Here's the game plan for today. We're going to start with the backstory, how Bitcoin even ended up with ECDSA. Then we'll dive into the three big problems this choice created. After that, we'll look at how these signatures are actually made. And to wrap it all up, we're going to take a real one apart, piece by piece.
So, first up, Bitcoin's accidental signature. You know, this is one of those classic tech stories where the best idea doesn't win. Instead, the one that's just there and ready to use takes the prize. It's a perfect example of how real-world circumstances shape innovation.
And that leads us to the big question, right? If there was a better way to do things, why on earth did Bitcoin launch with something that was, known to be second best? Well, the answer isn't about technology, really. It's all about patents and timing.
Okay, so let's jump in the time machine. Back in the early 90s, a brilliant cryptographer named Schnorr patented his signature algorithm, which was great for him, but it was a total roadblock for any open-source project. So what do clever developers do? They invent a workaround. They came up with DSA, and later the much better elliptic curve version, ECDSA. Flash forward to 2007, when Bitcoin is just getting started. ECDSA is free, it's open, and it's already in all the standard crypto libraries. It was the only real choice. It literally took until 2021 with a Taproot upgrade for Bitcoin to finally be able to use the technology it probably wanted all along.
So the bottom line is this: ECDSA wasn't chosen because it was the best. It became the standard for Bitcoin and so many other projects simply because it was what was available. It was the good enough tool that let the revolution get started without a legal battle.
But choosing the good enough option always has a price, doesn't it? So what were the trade-offs? Well, that brings us to our next section, the three big problems. Let's look at the hidden costs that came with this accidental choice.
And this table really lays it all out. Compared to the ideal, Schnorr signatures, ECDSA has some major drawbacks. First, complexity. It just takes more computational work to create and check a signature. Second, security. This one's a biggie. And third, flexibility. ECDSA signatures are non-linear, which is a fancy way of saying you can't easily and safely combine them, which makes cool stuff like multisigs way more complicated than they need to be. Let's just focus on that security point for a second. 30+ years. For over 3 decades, this algorithm that secures billions, if not trillions of dollars, has been operating without a complete published security proof. It's a long time to just kind of hope the math is sound. And this isn't just theoretical. The real-world consequences are serious. Because of that flexibility issue we mentioned, developers had to create complex workarounds. And as this quote highlights, that added complexity has, in some very famous cases, led to bugs that literally leaked people's private keys. So yeah, the stakes are incredibly high.
Okay, so we know the history and we know the problems, but how does this whole thing actually work under the hood? Let's jump into the mechanics of it. We're going to take a look at the math behind the magic, but don't worry, we'll keep it high level.
So at its core, what is a digital signature? It's just a chunk of math that proves a message is authentic and came from who it says it came from. In the world of ECDSA, that proof boils down to just two numbers. That's it, two values we call R and S. The whole complicated process is just about creating those two little numbers.
The signing process basically has 3 steps. Step 1, and this is absolutely the most critical part, is creating a secret one-time use number. We call it a nonce, or NK. If you ever reuse this number, your private key is toast. It's that serious. Step 2, we use that secret nonce to generate the first part of our signature, the R value. And finally, step 3, we calculate the S value by mixing together that nonce, the messenger signing, and your private key.
Now, here's the magic. The verification process is kind of the reverse, and anyone can do it. They just need your public key. They take the two signature values R and S, the original message, and your public key, and they plug it all into a formula. If the math works out and the answer matches the original R value, boom, the signature is valid. It proves you signed it without you ever showing your secret. Pretty cool, right?
So that's the theory. But what does one of these signatures look like out in the wild on the blockchain? Let's move to our final section and actually dissect one of those super long, intimidating strings of text you always see. And there it is, in all its glory. This is a real, raw ECDSA signature encoded in a format called DER. And yeah, I know, it just looks like a meaningless jumble of letters and numbers, like my cat walked across the keyboard. But I promise you, it's not random at all. Every single part of this string has a very specific job to do.
And check this out. This table breaks it all down. That crazy long string is really just a container, a little package with labels. It starts with the marker saying, hey, a signature starting. Then it tells you how long the whole thing is. Then it has a marker that says, okay, an integer is coming up, followed by the length of that integer, and then the R value itself. It does the exact same thing for the S value, and it all wraps up with a little suffix that says what type of hash was used. See, it's just a very structured, standardized way to pack up our two hero numbers, R and S.
So what's the big picture here? Well, it's that the technologies we depend on often have these messy, practical origin stories. Bitcoin's accidental signature wasn't born out of perfection. It was born from patent problems. And that choice had real trade-offs in complexity and security for over a decade. But, as we just saw, even that super intimidating string of data can be understood once you know it all boils down to just two numbers, R and S.
And that really leaves us with one final big question to chew on. ECDSA is the ultimate good enough solution that became a global standard. It kind of makes you wonder, right? If our entire digital world is built on foundations like this one, what other crucial compromises are out there, hiding in plain sight?